Hello everyone. So I hope you are enjoying the days. It rained a lot today. So let's start. So is my audio fine? Okay, great.
Yes.
Thank you for confirming. Just give me a minute. Right. So before we continue, do we have any questions from the previous lecture? Okay, great. So let's continue. We were talking about image filtering, and I think we stopped at derivative last time, so I will continue from there. So derivative, I think we covered this, so I will quickly go over this again, just in case you have any confusion. So this is the standard formula for computing a derivative. If you have a function f, and if you want to compute the derivative of this function with respect to x, this variable, so this function might be dependent on this variable, then what you do is you select a very small step, which is called delta x, and then you compute two different values. So the first value will be at the current location and the value of x, and then you will add this perturbation or subtract this perturbation from this value, and again compute the function value. So whatever the difference is in the response of this function, you take that and divide with the small step. So that's how you compute derivative. It's a very standard formula. And so let me skip these. These should be fine. Now the idea was, what if the step size is like not a very small limit? What if we just use a step size of 1, right? So then delta x can be replaced by 1. So then we don't have to worry about the denominator. It's gone. And in this delta x, you can just replace this with 1. So what you will get is x and negative of 1. All right. So if you think from an image or a matrix point of view, so if you are considering this location x, the value here is just like the value at the neighboring pixel or at the neighboring location in your matrix. So then essentially you can compute the derivative by just subtracting those consecutive values. All right. So that's what we get, and that's one, and that's just difference of two neighboring values, and that will be your derivative. And again, this is like an approximation. I think there is a question from Ruchi. Can you share the solution for homework 1? Yeah, sure. So we will do that later today. Okay. So let me check if, so Tao, are you there? Let me see. Okay, the TA is not here, but yeah, we will do it like later today. And if just in case I forget, just remind me, just send me an email. All right. Okay, so then what we can do is we can actually compute these derivatives in different directions. So the standard formula which we get, where what we're doing is we have the current location, which is x, and then we subtract 1. So it's kind of a previous location. So that's called backward difference. Similarly, what you can do is you can actually consider the next value, the next location, right? You can just add 1, and this is called forward difference. And later on, you will see like, okay, it doesn't matter like which one you're using, backward or forward, when we use like from a filtering point of view. The other variant is it's different from these two. In this case, what we are doing is if we have to compute like a derivative for current location, we actually ignore the value of that location. We just look at the neighboring values. So this is like the next value, and this is the previous value, and we subtract those, and that will give you the derivative. Okay, so this is central difference. Now, let's try to compute like these derivatives in this very simple example. So these arrays here, let's say these are the outcome or the response from this function f, and at these different locations. All right. Now we want to compute the first order derivative. So what we will do is at this location, you can just ignore it because it's kind of a corner case. All right. So because we don't have any value previous to this, so we just write 0. Okay, so don't worry about this corner case. Now, if you move to this location, you will subtract from the previous one, you get 5. You consider this location, you will get -5. And I think there is an echo, so if your mic is not on mute, please do that. Thank you. So these, is there a question? I think there's a student whose mic is not mute. Let me quickly check. Yep, it's okay now. Sorry about that. So if you consider this location, you can just subtract these two. So both are equal, you get a 0, and you can do like for all the other values. So you can see that computing derivative on this array, it's pretty straightforward. You just subtract subsequent numbers, and that will give you your first order derivative. Now what you can do is you can again compute a derivative of this array, right? So then that will be derivative of derivative, so that will be second order derivative. And again, it's the same thing. You can just ignore like the previous, you don't have anything, just put a 0 here, right? So 5 negative and 0, it will give you 5, negative 5, 5, that will give you 10, and so on and so forth. It's just like subtraction. Now an interesting thing, what you can do is you can actually come up with a derivative mask. All right, so instead of like doing all these subtractions, what if you have some kind of mask which you can apply at all the locations, and the result will be like the resultant array will be like a derivative. So for backward difference, we can write the mask something like this. So negative 1 1. For forward difference, it could be 1 and negative 1, and for central difference, it will be negative 1 0 and 1. So in this case, you can see that what you're doing is, if you're computing a derivative at this location, so if you put this mask at this location, so you are going to do element wise multiplication, and then you will just add those values. Okay, so that's how masking will work. So you can see that the previous element will get a negative 1, so it will just give it a negative sign because it's a number 1 here, and this will remain the same. And when you will add those, it will be like a kind of subtraction. So essentially, when you apply this mask on this array, you will get this first order derivative. Okay, so question from Fernando: is this backward difference? I don't know what you are referring. So yeah, this is the first, the second row here. This is backward difference. If that was your question. All right. So yes, go ahead.
These derivative masks, so we actually put the mask like a sliding window on this array of numbers, and then we add the numbers that are scaled by the values of this mask. That's how we get the derivatives?
Yes, exactly. So you take this mask and you put at this location, do element wise multiplication, sum those up, then put at this location. So you just keep putting this mask at different, all the possible locations actually.
All right, thank you.
Okay. So again, this is central difference. You can see that we don't care about what value you have in the current location because there's a 0. Whatever you have, it will turn into a 0. The previous is negative 1, the next is 1. You can just sum up those two values. So this was a derivative in one dimension, and of course what you can do is you can compute derivative in 2 dimension as well. And the formal definition will be like, so your function will have to be 2-dimensional function. It will take two different inputs, x and y, and this is like the operator which we use. So this is a gradient operator, and the way we compute gradient is, it's not like just one value. When you compute a derivative of a 2-dimensional function, you will get a vector. All right, so that's why we call it gradient vector. So it might sound like scary, but actually it's not. It's pretty simple. It's exactly the same way you were computing gradients in 1 dimension. So what you do here is you compute the derivative in 2. So the first value is like the partial derivative of the same function with respect to x. And this is similar to like computing derivative in 1 dimension. So that will be the first value in the vector. And then you compute partial derivative with respect to y. That will be second value. So, and these two values, you can put that as a vector here. So this fx is called partial derivative of f with respect to x. This fi is called partial derivative of f with respect to y. Okay, so it seems scary, but again, it's a normal derivative, the way you compute for one dimension. It's giving you two values, and that's why we call it a vector. Now you can do something more about this, because this is a vector. This is not just a value like you were getting in one-dimensional derivatives. So, but you can compute magnitude of this gradient, and the way to do that is you just compute under root and then square these values and sum those two values. All right. So this is kind of a Euclidean distance, the way you compute, similar to that. And then you also have orientation of this vector, because this is a vector, right? So it should have some direction. And the way you compute direction is you just take tan inverse fx over fy. All right. So these are standard equations. Let me see if there's a question. So a question from Carlos: the third value on double derivative of f should be -10. Okay, let me go back. It means you are paying attention and you are understanding the concept, so that's good. So the third value, this one, of course, yeah, that should be -10. So thanks for reminding. We'll make this correction. Okay, that's good. All right, so now similar to the way you computed derivative mask for one-dimensional derivatives, you can do similarly like for two-dimensional images as well. And in this case, you can see that it's a two-dimensional matrix, and this is like derivative in x direction. So you, for one dimension, just had like a -1 and 1, and for central difference it was -1, 0 and 1, right? So in this case, you just extend that like in the y-axis as well and just form a matrix. Okay, so this will be your derivative mask for x gradient, and similarly you will have a derivative mask for y gradient. This you can see that it's going in y direction. So this is the mask you had. It's the same mask, central difference mask, right? But again, it's going in y direction. So you just extend it to 3x3 matrix. So these masks will be really useful. You will see later on. Okay, so now let's try to apply these masks and compute actual derivatives on, let's say this is a image patch. So we are showing that in a form of a matrix here, and see like what these operators will do. So let's take like the x derivative mask here, and we put this mask at this location. All right. So then what we will do is we will just do element-wise multiplication and then sum all those values. So this is something which you will get. You can do the math minutes. It's fine. We don't have to go through like each computation, but essentially you are just doing element-wise multiplication of these two matrices and just summing those values and just putting at the center. Okay. So here you can see that what you get is you get high values in this column, right? And then high values in this column. Now, if you look at this matrix or this patch, so you can see that in these two columns, you have like all numbers are 10, right? And then suddenly, like starting from this column, all of the numbers become 20. So if you try to visualize like what's happening here, your intensity of the image is actually changing at this location. So your intensity is 10 here, it's 20 here, so it's kind of increasing. And if you look here, you see like a 0, so just ignore the border, but then you see like high change, right? And then everything is constant. So everything was constant, then you see a change, and then everything is a constant. So these numbers are kind of indicating that there was some change in this x direction when you move from left to right. All right, so we'll talk about that more. So a question from Fernando. We ended up with an array of the same size because we padded with the same value as the edges. Right, so for the edges, we just put 0 because we can't put like this matrix at this location, we don't have values here, right? So that's an issue. We'll talk about that as well. Okay. So right now, just assume that we put zeros in the borders and only these 9 values are computed. And still you can see that there was a bump here and then everything becomes 0. So this is derivative in x direction. Now let's see what we will get when we compute a derivative in y direction. Okay, so this is just showing it was computed. All right, so this was your mask for a y derivative. Again, you can put like on all these locations, right? So you can do the math, but what you will get is you will get everything as 0. Okay, and again, this is just element-wise multiplication, and you add those values. So in this case, you can see that you didn't get anything, and this is like in y direction, right? So if you look carefully at this particular patch, so in none of the column, the value is actually changing, right? If you look at this column, it's all 10, it's all 10, again, it's all 20, all 20, and all 20. So in the y direction, the intensity value was actually not changing. And that's why you are getting a 0, which means that this kind of mask or this derivative is trying to actually figure out if there is change in intensity in your input patch or in your input image. All right, so that is interesting. That we'll use later to compute edges in the image. So I think there's a question from Russia. You said the value changes from left to right, but the resultant matrix also depends on the derivative taken. Resultant matrix also depends on the derivative taken. Right. So I think you're talking about this x derivative. And when your value is changing from left to right, so this is your derivative operator, right? So if the value is changing, then you will get like some number here. It will be non-zero value. And the magnitude of that value will indicate like how much was the change. So in this case, if the change is just 10, right? It's going from 10 to 20. So that number 10 is indicating that amount, how much it actually changed. So was that the doubt, Ruchia? Is it clear now?
Yes, Professor, I had this doubt. So another question that I wanted to ask is, here we are considering the central derivative. So if we consider the other type of derivative, like the backward derivative or forward derivative, so will the same trend be seen even for that other derivative?
Yes. So again, so more or less it will be similar because both are computing derivatives, but the exact numbers might be different, and it will be different for different kind of inputs. So for this scenario, I think the number will remain same because these are kind of like flat matrices, right? All the values are 20 and all the values are 10, but in real world you will not have these perfect numbers. So there it will be different.
Okay.
So let's continue. So yeah, this was derivative in y direction, and it's all 0 because as I said, there is no change when you move like in the y direction. So before we talk about like why these derivative masks are useful and how we can use them to extract meaningful information from images, I have to cover this very important concept, average. You already might know this, and we have talked about this earlier as well. So mean, you all know, and we'll use this a lot. You have seen like even when we are computing derivative, we are doing element-wise multiplication, right? And then summing it up. But then sometimes we'll have to compute the mean. So it's like summing up is fine, but then mean is just dividing by the total number of values you have. So just be very handy about this formula because we're going to use it a lot. The other interesting concept which is related is weighted mean. So what we do here is, you might remember like when we were talking about the linear combination of columns, right? When we're talking about matrix multiplication. So it's somewhat relevant. So in this case, what you do is, for each number, you have some kind of weight. and then you add up all those values, and again you try to normalize by the total number of elements you have in your input. And if you think about when you're putting a derivative mask over an image, then essentially you are computing this weighted mean, because you are doing element wise multiplication, all right, and then you are dividing it by like the normalizing factor. So that's very much related. Now let me show you a very cool example of using those derivative masks on these real world images. So this is a sample image, all right? So this is a building and we have some trees here. Now what we can do is we can use those masks, the derivative mask which I showed you earlier for X and Y, and we can apply them on this image at every location, right? So we start from this location, we keep applying. So for each location, we will get an output, which we are showing here in this matrix. Okay. And so this C is, yeah, this is, I think, the X direction. So if you use your mask for X derivative, you will get this resultant matrix. And if you will use like the Y direction mask, you will get this. And you can see here that this is giving you all the vertical edges in your image, right? You can see like these pillars here, you can easily see all the pillars, right? All those are vertical. And the horizontal lines, like these borders, I mean, they are not present here, because these are like in the vertical direction, right? So if you use the Y derivative, you can see here, you are looking like all the edges in the Y direction. So which means that if you use those derivatives, you can actually extract edges in your input image, which is pretty cool, because it was a very simple operator. And this one here is, it's a bit complicated. We'll come to this later in the course. So this is like Laplacian operator. So this is double derivative. You can see that this is much better than these two. Okay, but again, this is based on derivative. All right, so now let's talk about correlation and convolutions. Both are almost similar things. So a correlation formula is like, if you have a function, if you have a filter, this is the operator, and this is the simple formula to compute the correlation. And this, I think, we have talked about like when we are talking about filtering. So for filtering, the formula you were using, that was correlation. So F is your image, H is your kernel, and this is the simple operator. You take the image patch, you take the filter, and you do element-wise multiplication, and then just add those values. So that's correlation. Convolution is almost similar. The only difference is you reverse your kernel, right? So you put a negative here. And if you do a X flip and a Y flip, which is like flip in X direction and flip in Y direction of this kernel, then essentially it's correlation. Then you can use the same formula. Exactly the same thing, right? You just have to flip your kernels because of these negative signs. Otherwise, correlation and convolution, it's doing the same thing. Okay, so some properties of convolution, it's associative. And so from technicality point of view, like a convolution, it's kind of a filtering operation. Okay, so what it does is, if you think like at a conceptual level, what it does is it's trying to find out like the amount of overlap you have between two different functions. So in this case, your functions are like your images and your filter. So convolution will just try to figure out if there is any overlap or not. Okay, so if there's an overlap, which means like they are kind of similar, it will give a very high response. If it's not overlapping, it will give you a very low response. So then you can think about like the way we were using derivative operators, we were putting on image and then trying to find the derivative, right? So whenever there was an edge, then you were getting a high response. So again, if you think, I mean, that's kind of just trying to find out the amount of overlap. So you are getting high response only when there is an edge. And if you carefully look at that filter, which I showed you, so this was -1, 0, and 1. So that's kind of an edge, right? Your values are changing. And correlation, as I said, like the formulation is almost similar, but it tries to find the similarity between two sets of data. Okay. So that's fine. That's just a technicality. Now let's move on to it's a very interesting filter. This is called Gaussian filter. And we have already talked about what a Gaussian function is. So actually this curve here, this is showing you a Gaussian curve. And this is the standard equation for a Gaussian distribution. Now what you can do is you can actually create a Gaussian filter out of this Gaussian distribution. And this is in 1 dimension, and this is in 2 dimension, right? So the way you create a filter is you try to discretize the value, and you know how discretization works, right? So you just break it like into different values and you use like certain values. So for example, if I have to create a 1D Gaussian filter, what I will do is I will just try to discretize this. So the center will become 1, right? And then I will pick 0.6 from maybe here, 0.6 from here, and then this is 0.13 maybe at this location, 0.0 from this location, right? So I'm just picking discrete values. And you can see that Gaussian, it's symmetric. So whatever values you have on the left, you will have similar values on the right. So this is 1D. Similarly, you can try to discretize the 2D version of this. Again, you can sample those points and create a 2D filter. Okay. And of course, like the center row of that and the vertical row will be exactly the same. You just have to find the rest of the values for that matrix. So this Gaussian distribution, this is actually quite interesting. So in the real world, like wherever you go, you will always see this Gaussian distribution. For example, like even in this class, we have 100 students, right? If I ask you to just share your height with me, right? And if I plot like a histogram of those all those numbers, the height, I will get a Gaussian curve. I mean, it will not be a very perfect curve, but it will be a very good approximation. So for example, here I'm showing you like a distribution of female shoe sales like from some company, right? So you can see, although it's not perfect Gaussian, but it looks like that. Okay, so it's like widely spread, and everywhere you go, you will find this Gaussian. You can pick like any distribution. Okay, so there are some nice properties about this Gaussian distribution. So first of all, it has infinite number of derivatives. Later we'll see like how that is very useful. It's symmetric, we have seen that. And again, Fourier transform, if you compute for the Gaussian, again you will get a Gaussian. And if you compute a convolution operation of Gaussian, again it's going to give you a Gaussian. Another interesting property is like separability. We're going to talk about that as well later. You will see, because if you have a 2D convolution, we can actually separate that into two 1D convolutions, right? So it's separable. And this is a very interesting fact. I mean, in an eye, like we have some cells which actually perform this Gaussian filtering. Okay. Now let's talk about like some more examples of filtering. So now we have covered a derivative, we have covered what filtering is, we have covered correlation, we have talked about convolution, and we know Gaussian distribution. Okay, so this is your input image. This is a grayscale image, and of course, you can use a RGB image as well. So now this is my filter, and in the excuse me, just give me a minute. All right, so this is our filter, and it's a 3x3 filter. We have 3 columns, 3 rows, and you can see that at the center I have 1, and all the other locations it's 0. So I will have to perform a filtering using this filter on this image. So what I will do is, again, I will take this filter, put at all the possible locations, and for each location I will get a number, and I will try to visualize that. So any guesses like what this filtering operation will do? Okay, so there are some comments, and I think Anshuman is right. Sayed is also right. So there will not be any change. So what's actually happening here is when you apply this filter at any location, you will multiply all the neighboring pixels with 0, right? So it's nullified, and you multiply the value of the current pixel with 1, which means you are just keeping that value. Okay, so when you apply this filter, it's not going to do anything. You will get the same image as output. Okay, so if you try to visualize this like in a 2-dimensional space, the filter will look something like this. Okay, so everything else you have 0, and at the center you have 1. So now let's look at like some other filters, and this is also very interesting. So in this one, you can see that all these locations are 0, even the center is 0. We have a 1 here. And so any guesses what will happen when we apply this filtering operation on this image? Right, so this is going to shift your image, and this is going to shift your image towards right, because what essentially you're doing is for each location, you are ignoring all these neighboring pixels. You are ignoring the current pixel, but you're just copying the pixel value from the left. So which means that all the pixel values will be copied from the left. So the image will be shifted towards right by 1 column. Okay. So that's good. It means you are understanding it. So it's just showing like shift towards right. And similarly, like if you have a 1 here, you can shift towards left. If you have a 1 here, you can shift towards bottom, and you can even shift like diagonally, right? So then now you know like how to perform shift operation using a filter. So you know which filter to use. Now this is a very interesting filter. You can see that we have 1 like everywhere. And one important thing here is we will always try to normalize our filter. Okay, so in the previous filters, you saw that, okay, if you just sum up these values, you will just get 1, right? So we don't need to normalize. But if it's like greater than 1, we'll have to normalize. So in this case, it's 9. So we normalize it. So the idea is like the sum of all the pixels should be 1. Now, in this case, what's going to happen is you are actually, if you are updating the value at this location, you are looking at all the neighboring pixels, you are looking at the current pixel as well, and then you will just divide that with 9. So you're kind of averaging out the intensity in a local neighborhood, and this neighborhood is 3 cross 3. So this will kind of do blurring, and some of you have commented, so that's right. Let me see if there was a question. So I think question from Fernando, image gets darker. You cannot say darker. It depends like what's the intensity, right? So it's just smoothing your image. So it makes sure that if you have like a very sharp pixels, which have intensity which differs a lot when you compare them with the neighboring pixels, you're going to average those out. Okay, so this will be the output. You can see that this is kind of a blur operation. Okay, so you're smoothing your pixels. And so that was 3 cross 3. And again, you can have a bigger filter. It doesn't have to be 3 cross 3. In this case, we are taking a 5 cross 5 filter. And again, we have like 1 everywhere. And you can see that the sum of all these locations will be 25. So we are trying to normalize the filter as well. Otherwise, what will happen is if you don't normalize, the intensity value of this image will change and everything will be like very bright. Okay, so we don't want to change that. So again, this is doing the same effect. It's smoothing your image or blurring your image, but in this case, it's looking at a bigger context, a bigger neighborhood, right? So the blurring effect will be like much more as compared to the previous one. So that's the result. I think there is a question from Amelia. Can you explain why in the previous example it shifts right and not left? Okay, let me go there. Okay, this one, right? So why the previous it shifts right and not left? So if you think about this, when you put this filter at any location, so you are placing the center there, right? So you are ignoring all these values. You are ignoring the current value. So when you will do element wise multiplication, you will only have value from this neighboring left pixel. So essentially the effect is like you take that pixel, they take that value and copy it here. So you're copying the value from left to right. And that's why the image is actually shifting from left to right. So Amelia, was that clear? Okay, great. Okay, so that's smoothing. And so this is the most interesting filter we have so far. And this is based on Gaussian. So this is called Gaussian smoothing. Now, if you compare like this filter with to like the actual Gaussian 2D Gaussian curve, which I showed you earlier, it resembles it, right? It's just like it's discrete. You can see like a high bump at the center and then values decreasing as you go to the border. Okay. So again, this is a bell-shaped curve, but in 2D. So again, this is going to perform smoothing, and you can see that the effect is much better as compared to the previous filter you used where everything was 1. Okay, so the reason is because you are paying more attention at the current intensity, the intensity of the current pixel, because the center is very high, and if you think about this from like a weighted average kind of perspective, then you are giving higher weight to the current location, and your weights are actually going down as you go towards the border, right? So that's another interpretation. So if you compare like the Gaussian smoothing with smoothing by averaging, this is your 5x5 filter where you have like all the values as 1. You can see this image is like much more better than this one. Okay, so now let's see what if we have noise in our image and how filtering can help. So in this case, we have added Gaussian noise. Okay, and this is the output after averaging. So this is like average filter, and this is after Gaussian filter, so Gaussian smoothing. You can see that this is like very, very blurry because you had a lot of noise here. But even in this case, it's not that good. You still have noise, but not as bad as this. The features are still preserved there. Okay, considering like the amount of noise you had, it's not bad. Okay, so question from Momal, what is Gaussian noise? So this we discussed in the previous lecture. So Gaussian noise is you have that Gaussian function, right? So you randomly at each pixel, you try to change the value of that pixel or the intensity of that pixel using the Gaussian distribution. So if you do that, that's called Gaussian noise. Okay, so Fernando, will it blur if we keep applying Gaussian smoothing? Yes, so if you can keep applying Gaussian and it will keep getting blurred, right? Yeah, it will keep happening. So that's true. Okay, so the operator or the filter which I showed you earlier, where every location has a value of 1, that's called box filter. All right. And what it's going to do is it's just replacing the pixel with the average of its neighborhood, right? That's what we discussed. So that's kind of averaging. Now let's try to actually look at the actual pixel values, how it's operating. So for example, let's say we have this image patch. Okay, so you have 0 like in the darker regions, then you have 90 like the pixels which are brighter, and you have a 90 over here, then a group of 90 over here. So what we are going to do is we're going to apply this filter at all the locations, all the possible locations. So we start from here. So that's the first location. Of course, we can't put this filter at this location because we don't have anything in the surrounding. So that's the first location. So that will give you a 0 because everything is 0. So you can keep doing that. Okay, so let's talk about this, right? So in this case, what will happen is you can see that some pixels are 0 and some pixels are like 90. So it's just going to take an average, which is going to be 50. And in this case, you can see that all the pixels are 90. So it's going to give you 90. All right. So again, you can see that it's kind of a smoothing effect. So your pixel intensities were like, in this case, it's kind of, you can say it was binary 0 and 90. But after this smoothing or box filter, you get something like this, which is kind of a smoothened image. And the most interesting thing is if you look at this location, So this is 90, and usually in real world we don't have such like artifacts, right? This is a huge contrast. So you can see that if you apply box filtering, it's pretty much gone from here. So it's very smooth. So it's kind of fixing noise. Okay, so I think there's a question from Anshuman. What is the difference between Gaussian blurring with large sigma and blurring multiple times with small sigma? Yeah, we will come to that. We haven't talked about sigma yet. Okay, but that's a pretty good question. I will have to think about that as well. So I have a slide later on. We can discuss it there. Okay, so it's kind of a smoothing effect, and it will try to remove sharp filters as I showed you here. Like this was a sharp feature, so it's all gone. And so this is like again one example where using this box filter, and of course this is like I think 5x5 or 7x7 filter. So all the edges and everything, it's gone. So it's very, very blurry image. So we need to be very careful, like what kind of operation we want to do, what's the result we want to obtain. Okay, so let's do some more filtering. So this is the original image. You might recognize like this eye, and this is again, you know, it won't change anything. And in this case, again, we have one on the right, so it's going to shift your image towards left, something like this. Okay. Now what you can do is you can actually combine different filters. So I think there is a question from Shibo. Will the box filter change the picture size since we ignore the border when we do the box filtering? So if you, it depends. I mean, you can ignore it. Then what will happen is like your resultant image will be like 2 pixels less in each dimension, right? Because of the border. And again, it will depend upon like what's your filter kernel size. If it's 3x3, then you will be losing like 1 pixels on each border. But usually if you fill it with 0, then it could be the same resolution. So we are going to talk about that as well. So just hold on. So it doesn't have to be just one filter. You can actually combine multiple filters. So in this case, you can see that this filter is again kind of trying to increase the intensity, right? Because it's just multiplying the intensity with 2. And this is the box filter, which is kind of a smoothing filter. So what we can do is we can subtract this box filter from this one. So if you think about this, this is trying to increase the intensity, and this is trying to smoothen out the image. So essentially the effect of this will be you're trying to push like the intensity of a pixel away from the neighboring pixels, right? Because you are increasing it and then you're subtracting the average. So you're pushing it away, and that's the intuition, and that's why it's called sharpening filter. You're sharpening your image, and you can see the result. And again, the pixel intensity, if you look at each location, it's actually kind of enhanced. Okay, so that's why it's called sharpening filter. It's pretty interesting. So that was the eye from this image. So this is the original image. If you apply that sharpening filter, that's the output, and you can see that it's kind of looks nice. Okay.
Professor?
Yes.
Why do we have to subtract that averaging filter from this first one filter to get the sharpening effect? Why not just the first filter with the 2 in the center and zeros around it would do the sharpening? Like just increasing the intensities won't help?
If you just increase the intensity, then you are increasing the intensity of each pixel, right? So what this sharpening filter is doing, it's trying to push like the intensity of the current pixel away from the intensity of the neighborhood. And that's how it's sharpening, right? That's subtraction here. If you just increase the intensity, then it's going to be like for every pixel, right? So every pixel will be bright. It will not be sharpening. It will be intensity enhancement.
So a 2D Gaussian filter with a very sharp peak could do that too?
A Gaussian filter with a sharp peak, I mean, there you don't have, I mean, that's just one filter. You will just average out the values. I mean, you are not contrasting them. you're not pushing them away, right? And in this case, you have this negative sign. So whatever average value you have, you are pushing that average away from the center location.
It makes sense. Thank you.
Right? So question from Michael, why would the two matrices be subtracted? So that's the whole idea, right? So this box filter is smoothing your image. So if you look at a local neighborhood, it's trying to figure out, okay, what's the average intensity in this region? And the first filter is just enhancing the intensity. So when you subtract those two, then you are looking into like, okay, how much is the difference of this current pixel with the average of the neighborhood? And that difference is the resultant value. So if the difference will be high, then it will be high intensity. If the difference will be low, it will be low intensity, right? That will increase the contrast. Okay, so that's called sharpening filter. And this is like Sobel filter. We'll talk about this later as well, later in the course. But let me quickly give you an intuition what this does. So you can see that it's trying to figure out like the edges in this image. Right? And if you compare this with like the derivative mask we had, it's kind of similar. The only difference is we have like the number 2 here, right? In the derivative mask, it was 1 all over. So 1 in this column and -1 in this column. So in this case, it's 2. And it's called Sobel filter. So that's pretty interesting result. So this is giving you vertical edge. But again, if you take a transpose of this and you have 1 to 1 in the first row and negative values in the last and 0 in the center, then it's going to compute your horizontal edges. Yeah, something like this. Okay, so these are some key properties of filters. So again, we saw that you can subtract 2 filters and then perform filtering. Of course, if you perform filtering independently, you will get 2 images. So I think that will be a good exercise for you if you want to try that out. You can just try box filter on the image first, and then just try to increase the intensity on the second image, and then just try to add those 2 images. So it will be the same result. So it's a shift invariance. So you can shift your images and perform filtering, or you can perform filtering and shift your images. It's not going to change anything. So it's a linear shift invariant. And the interesting thing is that if a filter is like linear shift invariant, you can represent that as a convolution. Okay, so these are some more properties. It's commutative, which is fine. It's associative. I think we have talked about this earlier. And again, it's distributive. And of course, like you can factor out the scalar. So if you have like some scalar value like in all the locations, you can just bring that out. So this is also useful like when you're trying to normalize your filter, right? You have that normalizing factor at the outside, but you can actually multiply that normalizing factor with all the values. So that will just change all the numbers. And this is just identity filter. We saw that earlier as well. It won't change anything. It will just give your image back. Okay, so another important filter before we conclude today is a median filter. And this is a very, very interesting filter. So what it's going to do is it's instead of replacing the current pixel value with the average, it's just going to replace with the median. And median, you all know like how to compute it, right, from your statistics class. So let's try to do that on this image. So this is like box filtering. So when we were applying box filtering at this location, so we were just averaging out all the numbers, right? And we got like something like 50. But let's say we want to use a median filter. Okay, so median, what will happen is you can see that we have a total of 9 values, right? 4 of them are 0 and 5 of them are 90. So median of this will be 90, right? So any question in that or any doubt? So the median will be 90. So you will just replace that with 90. If you guys don't know how to compute median, just let me know. We can quickly discuss that. A question from Fernando. Any reason to have a filter that isn't a square? There isn't any reason, but we want it to be symmetrical. Of course, you can have like a filter which is maybe odd shaped, 3x7, and it could be. But I think what's ideal is, first of all, it's due to efficiency. Later we will see, but we don't have filters. I mean, we can have, but we don't use like even numbers. For example, 20x20. Sorry, for example, 2x2. Right. So for 2x2, the issue will be like where you're going to place that filter. So if it's 2x2, it's going to cover these two 4-pixel values, right? But to which pixel you are actually attending, it's not clear. So then you'll have to make a decision, okay, whether it's going to be this pixel, or this pixel. If it's like, if it's an odd number, then it's pretty straightforward. For example, if it's 1x1, you know that it's just one location. If it's 3x3, again, you will have a center. Again, 7x7 and 5x5, you will always have a center. Okay, so that's why you will see like whatever filters you're using, they are mostly like odd shaped, not odd shaped, square shaped, but odd number of columns and rows. Okay, so I think there was a question from Amelia. What if we had 90, 45, 90, 95, 90? So then it will be, it won't be 90, then it will be 45. So median is like you take all the numbers in your array, you sort those arrays, and you pick the center number, right? So in this case, the center number will be 45. So then you will just replace that with 95, 45. Yeah, Curtis answered that. So that's right. You sort it and divide the two. Yeah, if it's an even number, you just like maybe divide those two or pick one. Okay, so now let's see like the effect of median filter in real images. So we had like this is the original image, and this is like the effect of mean filtering, and the filter size was 3x3. And this is, as we are increasing the filter size, you can see that it's improving, but again, it's causing a lot of blur. So in this image, it's pretty interesting. It's using mean filtering. All the noise is gone, but it's quite blurry. So the reason the noise is gone, because you are now looking at a bigger context, right? 7x7. So then all the noisy pixels will be like ignored. Not ignored, mean their effect will be minimized. That's why we don't see any noise here. So this is the effect of Gaussian filter. Again, like it's the same size, 3x3. As we move down, the size of the filter is increasing. And here you can see that the noise is not gone, even if we have 7x7. And the reason is because we have like those weights due to Gaussian distribution, right? The bordering pixels have very, very low weight. So that's why we are still seeing all these noises. But this is pretty interesting. The median filter, if you look carefully, even like a filter 3x3, you don't see any noise. It's gone, right? And as you increase the filter size, it's getting blurry, which is fine because it's trying to move pixel locations from one position to another, right? So that's causing this blur. But this was quite interesting, like just the 3x3 filter, all noise is gone. Now, one interesting question, okay, so if median filtering is that good, why don't we use it? So we still don't use median filtering, we still use Gaussian filtering or mean filtering, right? Yeah, this is salt and pepper noise. So anyone like who would like to answer this? I mean, even though median filter is giving you very good results, it's not used like in practical scenarios. Yeah, that's right. So Zubin answered that question because of sorting. So sorting is like expensive, and at each location you'll have to perform that. It's the best you can do is n log n. So that will increase the computation cost a lot. For other filters, it's just like taking the weighted mean. Okay, so that's the right answer. It's computation time. Now, yeah, there was a question, I think, about the value of sigma, the standard deviation. So ideally, if we have a Gaussian filter, so the question is like how big the filter should be. And the answer to that is, so these are like different Gaussian distributions. You can see here that, so different means and different standard deviations. So mean will tell you where is the center of this Gaussian distribution, right? For the blue curve, you can see mean is 0. So it will be symmetrical with respect to this point. Again, for the red, the mean is 0. Even for the yellow, the mean is 0. For the green, the mean is -2. So the mean will tell you where it's centered around. And the standard deviation, the sigma, will tell you how thick and how tall the Gaussian distribution is going to be. Okay, so if your standard deviation is high, so then it's going to be very thick bell-shaped curve, so something like this yellow, which means very high standard deviation. And if the standard deviation is very low, then it will be a very tall Gaussian. Okay, so whatever Gaussian function you use, the ground rule is what you want to do is when you're creating a filter out of this, you don't want these values, right? Because of course, when this Gaussian will extend towards -infinity on the left and +infinity towards the right. So if you look beyond, so let's focus on this blue one. If you look beyond, let's say -0.2, so everything is close to 0, right? So then we don't care about those values, because if it's all 0, then that's not useful. So what we do is we bound like a filter to this location where it's actually touching close to 0. Okay, and that is kind of about 3 sigma. Okay, so your filter is like set to half width of this 3 sigma. And that will ensure that, okay, whatever the border values in your filter are, they will be kind of non-zero, close to 0. And I think there was another question regarding padding. So that's let me see if there's a question. I think from Rajat. Here pixels are 0 to 255. Can't bucket sort be used since pixel have discrete values? Then, but again, you have to perform sorting, right? For other operations, you don't have to perform any sorting. And of course, you can optimize your sorting operation. Okay, so that's good. Now, we are concerned about the edges, what to do, like, because we can't place our filters on the corner. So one way is just ignore them, then your image resolution will reduce. But let's say we don't want to change the resolution of the images. So what we do is we need to do some kind of extrapolation. All right, and this will be like also useful when we come to deep learning and talk about convolution operation. Right, so there are different methods for extrapolation. The simplest one is we just black it out. We just like put 0 values. Okay, so it will look something like this. So you're just putting extra padding, and then what will happen is you will be able to put like your filter at the corners as well. It's just like the values it's picking, they are all 0. All right, so if you do that, and this is like the average operation, the blurring the box using the box filter, this is something which you will get. Okay, and you can then just ignore the border which you padded. So that's the final result. You can actually wrap around. So wrap around means you can bring the pixels from here and put it here, and bring the pixels from here and put it here. So you're wrapping it. And again, you can perform filtering, and that's the final effect. So essentially we'll see that all of these, like the result seems similar. So it doesn't matter like which kind of padding you use. It doesn't matter a lot. You can actually copy edges. So what you're doing is you're just taking the pixel intensity at this location and extrapolating towards left, like in all the locations. Again, almost similar result. You can perform reflection. It will be almost similar. Okay, so that's all I think I have for filtering today. And if we have any questions, I can take those.
Professor?
Yes, go ahead.
I had a quick question. When you were explaining the difference between convolution and correlation, you said for correlation we reverse the filter. Why do we do that?
Not for correlation. So correlation, you don't have that negative sign, right? You just multiply, use the actual values. For convolution, you'll have to reverse the filter. So let me actually go to that slide. 40 or something. Almost there. Yeah. Okay. So this is the equation for convolution, right? You
Right.
have a negative k and negative l. So when you do a x flip, then you are converting this sign. So this will become k. And when you do a y flip, you are negating this sign. Then essentially it becomes like filter k and l. And then you can use the correlation equation. And correlation equation, it's pretty simple.
Okay, right.
Right? So that's why we are flipping. And of course, I mean, if you don't want to flip, that's also fine.
Okay,
It's
that
just to
makes
show
sense.
that, yeah, it's just showing you the relation between convolution and correlation.
Um, so what is going to be the result is same for both, right? Or no?
Yeah, in this case, the result is same when you're flipping the filter, but it will depend on the filter. If so, there will be different scenarios, right? If your x flipping and y flipping is not going to change your filter, then the result will be same. But if it's going to change the filter, then the result will be different.
Okay, right. Thank you.
Okay, so I think a question from Anshuman. Are we taking the question now or some later lecture? Difference between Gaussian filter with large sigma and filter using small sigma but multiple times. So if you take a Gaussian filter with a large sigma, right, then I'm assuming that you are taking a bigger filter as well. Because if your filter size is same, then it doesn't matter like whether your sigma is big or not. So let's assume that you are taking a bigger sigma, and that's going to smoothen your pixel, right? Considering like more neighboring locations. And then you're comparing that with using small sigma but multiple times. I mean, both will be different, right? Because when you have a small sigma, then when you have a small sigma, I mean, you are essentially only considering those pixels. Let's say it's 3 cross 3. So only those pixels will be used to change the value. Your context is not growing. Right? So it will depend on like what will be your kernel size. It will depend upon.
Excuse me, sir. So
Yes.
let's say we are talking about 3 cross 3 in both the cases. So
Okay.
let's say I have a small sigma, so it means like I am giving more weightage to the center pixel as compared to the border pixels. And
Mhm.
once I'm performing them multiple times, then my pixels which are on borders will get more and more biased, while as the pixel which is the center will get less biased, right?
Right.
And what if I directly used some filter which had a large sigma, but just 3 cross 3, so that whatever I wanted, like give similar amount of bias to all the pixels, something like that. So we can
Okay,
reach.
so I think, yeah, I understand what you're saying. So you are saying that it's like it's the same kernel shape 3 cross 3, but in one
Yes.
scenario you are paying less attention to the center, more attention to the neighborhood, and in the other you are paying less attention or high attention to the center and less attention to the. So the difference will be, if you think about this, if you are performing like iterations of this filtering, right? So in each iteration, all the pixel values are changing. So in the
Okay.
next iteration, if you perform smoothing, then you're kind of propagating the intensity from not just the neighboring pixels, but from their neighbors as well. Because in the previous iteration, it was changed based on those, right? So
Yes.
it's kind of global averaging if you're performing this multiple times. But if you just do one step and a very high standard deviation, then that averaging will be like kind of local. You understand what I'm saying?
Yes, sir. Yes, sir. It's clear now. Thank you.
So I think there is a question from Fernando. When adding filters to RGB images, we normally stick to a 2D filter for each channel. Is there an example where we would like to have a 3D filter that takes input from all channels? I mean, of course, you can have 3D filter as well, right? So you can have a 3D filter and you can just perform it at the same time. So later when we will do deep learning, the convolutional neural networks, there you will see like we have these 3D filters, right? You don't have to perform filtering independently on each channel. So I mean the way, so earlier we studied 1D filter, right? We easily extended that to 2D filter. Similarly, you can extend that to 3D filter as well. So then it's looking into like multiple dimensions. And again, you just average those values. So I hope, Fernando, that was clear. If not, please let me know. I think there's a question from Tristan. When you have an image with multiple channels, for example, RGB3, do perform matrices operations separately and then add the channels back together. Yes, that's correct. So for RGB, like if you have to perform filtering, then you will filter like each channel separately. And then that will give you like independent channels, right? And then you can just concat those. That's going to give you RGB. So again, I mean, all of this, it depends like what exactly you want to do. Right, so if your aim is to perform, let's say, edge detection, which we are going to talk about in the next lecture, then ideally like what we do is we can convert like RGB images to grayscale and then just perform filtering on that, or we can perform filtering on all these RGB channels separately and then add the edges like later on. So for edge detection, that's all we do. But if we think about like filtering from deep learning point of view, then we don't do that. We just filter like at once. We just use a 3D filter and try to like combine them together. Okay. So yeah, question from Fernando. I understand we can do the math with 3D filters, but will we actually get meaningful data like getting edges or blur, etc. in 2D filters? For 3D, I don't see why won't you get edges, right? So that will depend upon like what kind of filter you are getting. Sorry, what kind of filter you are using. If that's a filter for edge detection, it will still be able to give you edges. So that will be kind of, so let me give you a simple example. Okay, so let's say you have an RGB image, like 3 channels, and then you're using a derivative mask, which is meant to compute derivative in, let's say, 2 dimension, like single channel. And then we can extend that to like a 3rd dimension. And if that 3rd dimension is meant to just compute average, then what will happen is essentially like you are computing edges in each channel separately. And then when you take average, you are kind of averaging, okay, what's the edge strength coming from each channel, right? You just average those out. So it all depends upon like what kind of filter you use. All right, so any other question before we end? Okay, so question from Rajat. For a K cross K filter, we are gonna have K square additions and K square multiplications. But for a median filter with bucket sort, shouldn't it be K square? But again, it depends upon like the size of your K. Right? If your K is, let's say 1, then it will be different. If your K is 9, then it's going to change. All right, so if there is no other question, let's end it here. And of course, feel free to contact me. Let me know if you have any other question later. Right? Thank you. Bye. Okay, question from Rusha. Is it possible to discuss homework? So yeah, I will say like come to office hours. We can do there. Okay,